Good morning, everyone. This is Jim Chastain with EasyPower. Welcome to our Tuesday refresher. Today's session's a little bit different in that we're trying to be as reactive as possible to the audience's needs, and I appreciate everyone for attending today. As we usually try to do, we like to start with a couple poll questions, get some feedback if you wouldn't mind. Today we're asking which part of the arc flash study represents the most difficulty for you, and then in presenting the reports, which area of that is most difficult. So we'd appreciate your feedback. If you would please respond in terms of indicating on the screen. This helps both in guiding the conversation today and in helping you get additional support and using the tool. So we'll leave this open for about another 15 seconds, get everyone's feedback. One of the things I'd like to emphasize during this conversation is that a primary focus of what our tech support team and quite literally the whole company is here for is to make sure that you're successful with the tools. And so where we can improve that effort, we'd like to do so. So it looks like we have at least a plurality here of responding. So I'm going to close this gate and show you how people are responding. I appreciate the feedback. And then let's go to our second question. Which part of the reporting structure is most difficult for you, or the final deliverables for your clients? Your feedback is not binding in any respect. We just want to have this as a reference point as we're going through some of this discussion. Now, the agenda today is going to, like I say, focus around primarily what we're being asked and questions from the audience. And here's how the response was here. And obviously this is not a surprise in any regard. That's why we're having this session. All right, let's jump into the agenda for today. So primarily, we're going to spend the next 30 minutes talking about questions that have been submitted over time. Very often in working with customers, new tool owners, we have a lot of questions that indicate, repeat questions that indicate there's some areas of common need in people using the tools. And sometimes these are new users and sometimes experienced users, and they may be just features that they haven't used before. So we will be covering questions about the tools, about the systems, and about using the tools for analysis. I would like to mention that as a new company or a new tool is purchased, we offer a Power Start tool for new owners, which is a 1-hour orientation session. And the idea, again, is to make your first project as painless as possible and make sure that you understand how to access tech support and you're confident with your ability to not only ask questions but get responses that are useful to you. I'd also like to mention that that same offering of Power Start, a 1-hour orientation, is available for new employees of tool owners that have a current maintenance agreement on their tools. So again, much of our priority, at least on this side of the telephone line, is to help you be successful with the tools. So as we're going through this, you're more than welcome to ask questions, enter questions on the question chat box, and we'll try to incorporate that in our discussion. So the first question, and a common question that comes up, is how do I update the device library? If you're on the distribution list for the EasyPower notice, EasyPower newsletter, each month we announce an updated device library that includes all new devices that have been added on the previous month. And part of that is by virtue of the fact that we're adding components as manufacturers develop new ones and want us to include their elements in our device library. And then and we include those as we have time and bandwidth to do so. But frankly, more frequently, our priority is for people that are doing projects and for some reason they have or are not able to find a device in their system or in their project that's not included in the library. And so when that's the case, if you can supply the data sheet, we would be more than happy to create the model and supply it to you within 48 hours to include in your study, but then it will also be added to the library for the next monthly update. So what I want to walk through real quickly is how you as a tool owner can access that that information. And so what I'm referring to, or what I'm going to be reciting here, is an entry in the knowledge base section of the EasyPower, which is relatively new to the website and growing. And I'm going to show you that as I kind of get through the PowerPoint. Step one is to make a copy of your current device library, especially if you have any customized data. And to do that, I want to show you where the library is located. It's under My Documents, EasyPower 9.8 Device Library. And what I'm going to do is go in and make a copy of the standardlib.mdb, then locate the serial number from my tool, close EasyPower, go to this location on the website, enter the serial number and submit it. And at that point, we can select the updates that we need. This update will then be downloaded into our machine as an exe file. And when we run it, it will update that entry in the library. We also, if we have a customized part of our old library we want to save, we want to utilize the library import utility. And then by running it, it will allow us to bring in the differences between the new library and the old library so we don't overwrite any of our customized changes. So let me see if I can kind of walk through this real quickly. Okay, so first of all, I want to look at the EasyPower homepage. If I go to support, technical support, I see a EasyPower knowledge base. I encourage anyone, any new users especially, to be familiar with this because there is a growing list of responses when people have asked questions on exactly this type of a dialogue. And one of these questions is, how do I update my latest EasyPower version? And then how do I update the library, the device library? So that's what we're going to do right now. And if you go into this particular location, it'll describe each of the steps that I just described. All right, so first of all, I want to go into my tools, the update section, and by so doing, this tells me, this checks with the version of the tool code that I have, and it tells me that I've updated, in this case, the February version of 2017 of the device library. So chances are I need to update my library. So to do that, I'm going to, first of all, go to my About EasyPower, write down my serial number, close out of EasyPower, go into my browser, and then the location I want to go to is, I need to go back to my slide presentation. The location I want to go to is this EasyPower/com support updates_login. And to do it off of here, I'm going to do Control-C. Okay, so then I put in my serial number, submit, and this takes me to the EasyPower updates page. Now, what I just checked in the tool status told me that I have the latest version of EasyPower 9.8, so I'm not worried about this. What I'm looking at is the library update. It's telling me that my library, the most recent, is dated May 20, 2017. So what I want to do is go out to my installation. I'm going to go to a equipment or a web Windows browser, go under My Documents, EasyPower 9.8, Device Library is located right here. If I open it up, there's a standard lib.mdb. When I download and update it, this file is going to be overwritten. So I'm going to right click, create a copy, and as it does, it renames it, so I realize that I can go back to it if I have a problem. Now I'm going to download the EasyPower Library 2017, and as I do that, my Windows says, okay, it's downloading this executable file, and when that completes, I launch it. Clearly there's going to be a firewall. I have to let it know that it's okay to go around my firewall. Here's where it's going to extract it, so we're going to go ahead and extract that. We're going to, looks like I've done it before, so we're going to go ahead, I've done it last year. So we're going to go ahead and modify it. Now, the other tool that I mentioned earlier was called the library import utility, and what's going to happen there, what I need to happen is I want to download this resource because this is going to allow me to compare the old versus the new, and you can see I've done it before, so let's go ahead and save it. And again, it's going to allow me to compare any element of the old library with the new library and then import them or import the changes that I've made in my original library. So once I've installed the library, I go back and look at so now it wants from the old library to the new library. So we're looking at EasyPower 9.8, device library. My old one will be the copy, and my new one will be the one we just installed. And technically it hasn't been installed yet because I'm going to be overwriting into the library. And then I asked it for, I think I've done panel schedules, and I can check them all if I want. It compares them, and obviously the more I check, the longer this is going to take, but it'll compare any changes and import the changes into the new library, so I've been able to save my customization. So this is going to take a while. I'm thinking I'll bomb out of this. So the point is, as I've made changes to my device library, if I import the new library, it's going to overwrite those. So I've created a copy, and then I compare the old one to the new one, and it will carry the customized versions to be included and not cause a problem with devices that I've saved or customized on my own. All right, so if there's any questions, let me know. This is all stuff that's, like I say, common to all of us, and it's not something we talk about very often. So anyway, as long as you have a serial number that's been, maintenance has been current, you're able to utilize that utility. Next, what to do with arc flash, high arc flash energy and low voltage systems. So this is a fairly common problem. Turns out in IEEE 1584-2002, there's a paragraph that says, while the accuracy of the model at 208 volts is not in the same class with the accuracy at 250 volts and higher, it will work and yield conservative results. What that means is the results at 208 volts will be higher energy than what's really represented by the physical system. Arc flash hazards need only be considered for large 208 volt systems. Any system fed by smaller than 125 kVA should not be a concern. So if I have a 125 kVA system, what do? And what I'm about to cover is also covered in the applications note in the handout section of this webinar, and it's called Calculating Arc Flash for Low Voltage Systems. So let's jump into EasyPower and talk about this. course, now I need to launch EasyPower again if I haven't hosed my installation. And let's open up the one lines that are in my user examples. So here's a typical situation where we have a 30 kVA transformer. We want to do arc flash. We need to make a choice on what to do about this panel. We've agreed with the customer that they're going to label everything 208 volts and up. So we're going to do a short circuit, change the short circuit focus. Let's fault this particular bus. And what we see is indicating 40.9 arc flitch boundary, instant energy 4.6. If we look at the arrange for arc flash, which gives us the calculations on the one line and the display of how the calculations were made, we see that the upstream device is BL4, that the air gap is a 25 millimeter air gap, the bolted fault current is 1400 amps, we have less than 1000 amps arcing current, and the trip time is over 1.73 seconds. Now the reason for this is that BL4 is up here in the primary, and if we look at the current, we can see that it's only seeing in the primary side of the system, it's only seeing 643 amps, and that's bolted fault current. So if we have an arc, the arcing current will even be less, and that's the reason that this is taking so long to trip. Well, the bottom line and what our application notes indicate, below 125 kVA, these numbers are artificially higher, unnecessarily conservative. So what we're going to do is going to short circuit options, look at my arc flash hazard controls, and what the recommendation is for this application note is anything that's less than 250 volts in this kind of a situation, we can limit the calculation time to 2 seconds or less. And in this case, the calculation of the arcing time is 1.73 seconds, and it's only 968 amps. Testing has shown that below 125 kVA, 240 volts or less, even though the arc may be initiated, it will self-extinguish in less than 300 milliseconds. So an engineering judgment applied to this situation, I feel there's literally 100% guard band in this situation to limit my calculations to half a second. So let's apply this. Let's go ahead and close this out. Fault this current again, look at my instant energy, and so now what I've done, I'm able to display by limiting the arcing time to half a second, and again testing shows this the arc would have extinguished at 300 milliseconds on its own under these conditions. Then I'm safe in predicting that the maximum worst case incident energy is 1.6 calories per square centimeter. And so now that's what I want to label this particular load. Any questions about that? Anybody have a problem with that? So yeah, I got a question here. Can the utility be used to import from older versions? The answer is yes. And so the question is, back on the import, the library is only maintained for 9.7 and 9.8. I don't believe it's maintained for 9.5. And so the answer is yes for 9.7. Any updates to 9.5, it will update any patches or any fixes from that generation, but I don't believe we maintain the library. If you have a special need in that case, it's worth contacting tech support and seeing if we can work out what your problem is. But again, as long as you have, yeah. So the next question, for the 208 volt panel, how did I come up with the 0.5 seconds for max time? In the application note that's in the handout section of the control box for this webinar, there's test results that IEEE reported that shows any arc, at least the minimum number of tests that they did, the limited number of tests, below 125 kVA and less than 240 volts, an arc could be initiated but would self-extinguish, and no arc lasted more than 300 milliseconds. So in my estimation and knowing what I know about my system, on any transformer that's less than 125 kVA, I feel comfortable in recommending a maximum calculation time of half a second, which is about 80% guard band over the 300 millisecond number. So that's how I came up with that number. Now I'm going to talk later on how to handle something beyond the 300 kVA. So let's jump into that. Okay, so the apps note covers the details on this. What to do about no valid upstream device. What I'm talking about here is, in fact, almost invariably a new tool user will forget to populate all of their protective devices in their one line. And so when that happens, there could be a number of problems or number of sources for the problem. And here's what I would recommend as kind of a catch-all in determining where my problem exists. So I'm looking at a bus here. I've drawn my one-line diagram. We're going to fault the bus, go into short circuit focus. Now clearly this potentially could happen with any bus or a number of buses. I'm going to fault this bus, arrange for arc flash, and at least in this bus, a 480 volt bus, it says there's no valid trip device found upstream. Well, that could be, if I look at this, the source, this is the main breaker coming out of the system. Somewhere between this bus and the utility, I do not have a protective device. So let me go find, I've located the utility. So what I suggest is, all right, is it a problem with wiring or is it a problem with devices? What I suggest as a test point is to put a utility fuse, insert a utility fuse right here at the location what is causing the problem, or where I have my utility source, and enter data that I know works and is complete. And by doing that, I'm going to look at this fuse. It looks like I'm at the 13 kV range. My go-to what if is going to be a AB chance fuse link Model T, and let's go ahead and set it for 20 amps. Now just pull this out of the air. The point is, when I go back to my bus that's giving me problems, if this works, then I know I've made a mistake as far as any protective devices. So I'm going to go to short circuit focus. We're going to fault this bus, look at the incident energy, and sure enough, I'm getting results now, and it's telling me that the fuse I just entered is the one that's being used to calculate the numbers. So what that tells me is virtually, so then the next question is, why didn't this breaker protect the bus? If I go to my short circuit options, you can see that I have indicated that I want to exclude the main breaker on each bus. So the tool is doing what I'm telling it to do. What's missing now, I need to go trace this one leg back all the way to my source and find out why my protective devices aren't doing their job. Well, it turns out in this particular case, if I go back to the utility, there's a fuse right there. Why isn't it working? And sure enough, just looking at it, it looks like I've entered the data for two of the sister fuses, but not for this one. So at this point, I'm going to take this one out, the one that I threw in there, and go back and verify. And it turns out, I think in this particular case, they use exactly the same fuse. So I'm going to copy and paste. and questions, the answer is problem solved. I go back to my bus, short the bus, short circuit, look at incident energy, and we're off and running. Okay, so that's it. It comes up a lot, and that's just the way I would troubleshoot it. Okay, now here's a situation where we're getting high energy and greater than 125 kVA, so it doesn't qualify for this calculated time reduction. What should we do? So let's give this a shot. No, I got another question. Any reason to use the panel schedule instead of a bus individual breakers? Brian's saying there's any reason to use the panel schedule instead of a bus with individual breakers. Apart from being able to generate panel schedules, the panel schedule object is kind of hard to step through and populate, but perhaps there are uses for the schedule apart from generating panel schedules and demand loads. Great question, and let me address this while we're going into this same topic. So I think Brian's asking why use a panel schedule or the icon for the panel schedule as opposed to a discrete representation of the panel with individual breakers. And there are, let me kind of come to my example here. There are some specific reasons that I might want to use a schedule over a discrete representation of the bus. All right, for starters, let's talk about that for a starting point. There's the primary reason, I think, for using a discrete representation of a panel as opposed to the icon is that it limits the number of buses that are in my system. And if I'm bus limited, or if I'm trying to keep the costs down, I can use the panel icons instead of discrete bus representation to do that. So that's one. Another reason to use the spreadsheet or the icon for a bus, let me go ahead and put one in here, is let's say I have, so the primary one is just ease of use. If I have a lot of panels, it's easier to, and they're loaded similarly, it's easy to cut and paste and take a loaded panel over and represent it and then develop the panel schedule. The disadvantage is by using the panel icon and the panel schedule, I do not get calculations down to the individual loads. So if I have a load on this panel that I want to represent or get a arc flash calculation for, I need to represent it as an outbound load. So let's say we've got a motor hanging out here that's 240 volts. I didn't mean to do that. Let's hook this baby back up. Put my motor down there. So now if this motor is run out of the this panel, let's kind of just make some numbers up here. The only way I can get a arc flash label on that load is to outboard it from a panel or to represent it as a discrete load from the discrete panel. So let's say if we have a 20 horsepower motor, and I go in and look at my panel description. Let's say we have 6 circuits. One of those circuits needs to be a sub panel, and at that point I pick out which cable it's going to, and it'll give me if I have a sub panel down there, or as I go over and look at what's loaded, it knows which cable I'm connected to, but it doesn't know what that load is. So I need to designate, when I go to size up that breaker, I need to designate inside the panel structure what the characteristics of this particular breaker need to be. And consequently, by, let's say, setting this up for 30 amps, now we can create a downstream arc flash label even though I'm using a panel schedule. All right, so the trade-offs are, when I use a panel schedule, I don't get labels for each load, and the upside is I reduce the number of buses in my total bus count by using a panel schedule or an MCC for that matter, which could be 20 or 30 loads, and remove that many buses from my total count. Okay, I probably beat that one into the ground. The answer that you were looking for, Brian, I think was yes. So it works either way. All right, so the issue here is I'm coming off of a 208 volt panel, and if we look at how big this transformer is, it's actually a 500 kVA. So this system doesn't qualify for the time limit on the calculations. And so when I go out here and look at the incident energy, what we're looking at is bolted fault current of 20,000 amps. So there's a real 6,500 amps consumed in an arc. And we still have this issue of a trip time for the breaker, or the fuse in this case, which is in the primary side of the transformer. And that's what's causing my high incident energy for this bus. So if you read the 2-second rule, and I'm not a fan of the 2-second rule, but in this case, there is a possibility for the 2-second rule being applied to the system, and the way I would do it wouldn't be on the whole voltage. I'd be doing it on this bus alone. We'd apply 2 seconds as a maximum calculation time based upon this bus. And even with that, we're looking at a potential 50-calorie calculation. So the issue here is the fact that this is probably an older installation, and we have a primary fuse protecting a remote device, and it's not adequate. If we look at an individual load fed from one of these lower voltage fuses, we see we have reasonable energy down here, and the reason that one's so high is I'm not sure, because I haven't finished populating it. But the point is, on the 2.8 volt side, as long as I have my fuses on the secondary side, they can be properly scaled for these loads. So the real solution has nothing to do with limiting time. It has to do with recommending a secondary protection scheme that includes the loads in the 208 volt system. Does that make sense? The main consideration here, again, when we're looking at our short circuit options, because we've designated everything to include exclude the main breaker, we want to make sure that the fuse that's used for that protection is outside or has a flash barrier between the incoming connections and this bus hot if we're going to be working on this bus. I think I muddled that up, but hopefully you guys got something out of that. Can you calculate cable resistance of all the cables at once instead of going to each cable? That's a good one. So the question is, can I calculate all the cables at once instead of going to each one? The answer is I cannot calculate them individually. I can calculate them in total based upon what my impedance is. So what we're looking at, if I look at fault current, let's say for this particular device, I don't want options, I want to go to short circuit current, fault this bus. So this 7,000 amps represents the voltage applied from this transformer and all the impedance between it and the utility source. So I guess what I'm suggesting is you have to do the math to know the total impedance path from here to the source of the energy. So I'm not sure that that was all that exotic, but aside from doing the individual cable calculations, that's what's done. Now, so the other alternative is to use power flow and do the same thing. In power flow, we solve the equation, and we're getting overloads. The point here will be the current that's, oh, there's no load. So yeah, I've got to have a load, and that load flow represents the total impedance of the leg. So I've got something going on down here because I've created the load, and these numbers will give me the ability to calculate the impedance. Aside from that, it's not something I can do with the tools. All right, so where does that leave me? I've got high voltages, high energy level, greater than 125 kVA. It's a real problem, and the correct answer is not to limit the time, but to relocate or locate new protection that actually works on the secondary side of the transformer. And this was kind of a neat question that came up in this last week. How do you display two energy levels on the one-line diagram? And the answer is pretty much like the impedance question. You cannot display two of them, even though, let's kind of talk about this for a second. What I'm able to do on my short circuit display is show the instant energy on this bus. Let's find a bus that has, here we go. So on this bus, I can fault the bus, calculate incident energy, which is very high, apparently. Maybe it's not even specified. And if I say calculate both excluding and including the main, the tool will show me two different numbers. All right, so there's, based upon whether this breaker is included or excluded, I get two different values of incident energy. Now, that's not what the question was. The question was, if I have two different sources of energy, in this case a standby generator and a utility, and I get much higher incident energy from the standby generator because the currents are lower, how can I display that? What I would suggest, or what I did suggest in this particular case, is rather than trying to do my both sources thing, let's stay with my basic setting, is on my one-line diagram, I insert a note with a leader that points out the area that I want to have extra information added. And what it amounts to is there were two different scenarios, a scenario with and a scenario without the energy from the generator. So go ahead and fault the bus. And let's say this was the generator display. Go ahead and with Snagit or with some sort of a window snipper, take a copy of this and then keep this to the side. Let's go back to my database. And then I'll put my label in here. So in our arc flash ratings, we may label for the generator rating because the generator is higher, or worst case, or I can rate it with the utility and then insert my label contents for the generator. In either case, my label will be different than what the one line tells me. Does that make sense? So when I go to my short circuit, fault all the buses, print out my report right here with the printer, in which case I'd print to a PDF, and then I'd paste the PDF, the new value in here, which will be different from whatever I'm calculating for the utility. So so that's one way to do it. The other alternative is to have a printout for each scenario and then just deliver a stack of prints for the electricians to look at to verify which type of configuration they're in. Can you calculate a TCC which would be independent of the changes made in the model? In other words, you create a TCC for a low voltage and then you change the settings, but you want to show both curves before the change and after the change. Let's give that a shot. Let's kind of go back to close this and open up an example that has some. So now if I understand the question, we're wanting to show before and after changes to a setting in a low voltage power circuit breaker. And let's kind of select this bus and this breaker, plot, go to coordination, plot the curves, and expand this a little bit so I can look at it. So well, what if I wanted to make a change or I want to compare both curves? Two ways to do it. I could actually insert a new curve for exactly the same device. So let's try this out. So an AC low voltage solid state trip, and let's make it the same thing. So it's a GE AKR 75. You kind of get the idea of where I'm going with this, and we'll set it up with the same setup, and I'll set it with the different settings. And right now I don't know what the other settings are, but I'm kind of winging it. All right, so this gives me the ability to show both settings, and I just make the settings on the second one to reflect whatever it was I wanted to change these, and I guess I could check it out right here. So the answer is yes, I can do both and be able to show that in my display. Hopefully that answers the question. Okay, we're running long. I apologize for getting down in the weeds on some of this, but it seemed like it was helpful. And I think I only missed one of my questions. So what I would offer, oh, and the other thing was you could actually put on the label a QR code that you could scan and reflect this information to the electrician. If he scanned the QR code, you could show what the alternatives PPE would be if he were on the generator, for instance. All right, so I think we're probably as good as I can manage on this. Thank you for attending. Check the website for updated schedules of newly scheduled webinars for regional training that's set up for the next 6 months. May is a designated safety month, so check for sales for special discounts on tools and upgrades. By all means, if you are a new tool owner or you are a new employee for an existing tool owner, contact EasyPower Sales to set up a power start. Any questions that you may have on any of the aspects of the tools, by all means contact tech support at easypower.com, and appreciate your support. Any questions I wasn't able to get to, we will cover email offline. Thank you for attending.